Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to continue our conversation for differential calculus on secant lines and then tangent lines. In fact, we're graduating into tangent lines at this moment. You must be pretty strongly familiar with all of algebra and trig and stuff like that before you start into calculus. That's just a heads up. I'm sure you already know that. All right, so let's talk about tangent lines. The definition of the tangent line goes as follows. The tangent line for a curve at the point x comma y is a line intersecting the curve at that point where the slope of the tangent line is equivalent to the quote-unquote slope of the curve at that point. Now that is a very ugly definition because there's a lot of pieces that you have to kind of tear apart to really truthfully understand it. In essence, what that definition is stating is that if you have some function like this here, this function f, if we had some anchor point. Now, in the previous video, I called my anchor point a comma f of a, and I really would have loved it if I had written that definition, this definition that way as well. It would have been very nice. So that's what I'm going to do here. I'm just going to say, suppose we have an anchor point, a comma f of a. I'll anchor it right here, in fact. And by definition, the tangent line for the curve f at that point is the line intersecting the curve at that point, a comma f of a, where the slope of the tangent line is equivalent to the quote-unquote slope of the curve at that point. It is basically this line right here. Let me zoom in so you can really see it. Let me get that back there. It's essentially the line that, well, technically is tangent to that curve, although I wouldn't want to use the definition tangent within the definition of the tangent, but that is actually true. It is a line that is tangent to the curve at that very moment. It intersects locally, although the way of drawing it doesn't look like that, but it intersects locally just once at that moment. There we go. It's a little bit better. Not perfect, but whatever. But a tire on the ground is tangent to the ground when it touches, or where it touches. So right here, there's my red tire. It is the ground is tangent to the tire when the tire and the ground meet, as long as it's a very, very rigid tire. That is actually true. Now, it should be noted that I am abusing the definition of slope here. In reality, only lines have slopes. Curves do not have slopes. They have something else, but it's not called a slope. So when I say, oh, the tangent line is the line that has the same slope of the curve as the curve does at that point a comma f of a, that's a little bit of an abusive notation or wording because, again, curves technically do not have slopes. Lines do. Now, our job is to recreate the tangent line by using a little bit of ingenuity. So if you're watching these videos in the order that I've recorded them, the previous video, the one right before this, is all about secant lines. And there was an example in that video that required us to find the slope of the secant line as x got really close to 2 pi over 3. Let's go ahead and find that. That would be this one right here, where we use Desmos to investigate the average rate of change for the function f of x equals 2 cosecant of 1/2 x minus pi over 6 plus 1. And we wanted our values to get super close to 2 pi over 3. Let's go ahead and take a look at that again in Desmos. Recall from the previous example here, which we have all queued up right now, that we were creating secant lines between 2 pi over 3 comma f of 2 pi over 3 and some other point on the curve. And as we drag that other point on the curve closer and closer to that anchor point at x equals 2 pi over 3, we started to get a line that became closer and closer to what we would call the tangent line at x equals 2 pi over 3 for this given curve. And to find the slope of that tangent line, we ended up building a table of values. Although you could technically, over to the left here, see that as we drag this point closer, our slope computations here can be seen to become closer and closer to -3 and some change. But unfortunately, the level of granularity that we're going to get from just dragging a point is not good enough. You can see that it's not really perfect. It gets close though, right? -3.4543 right there. However, building a table is usually a better idea. So building a table of values here, you can see that as the wiggled point away from 2 pi over 3 gets closer and closer to 2 pi over 3, the slope function that we have written here from last video gives us values for the slope that approach -3.464. So that is what we would consider to be the slope of our tangent line. And of course, if you're asked to round to, let's say, 4 or 5 decimal places, you'll need a lot more accuracy in Desmos for that. But that's how we could do that by hand. Again, just allowing those 2 points to get really close to one another so that we can estimate that slope of the tangent line. Now remember, in the previous video, we talked about the average rate of change, and the average rate of change was just the slope of the line connecting 2 points on a curve. It was the slope of the secant line. In this case, we're going to talk about the instantaneous rate of change. The instantaneous rate of change of a function at some anchor point a, f of a is the slope of the tangent line at a, f at a. In practice, rather than computing the slope itself, it's much easier to compute this version, where h is allowed to go to 0. It's just the distance between a and b, and we're allowing b to get really close to a. Let me say that again. If b is equal to a plus a little bit of a wiggle, that's actually what h is. H is just a wiggle. So if b is allowed to be just the value of a plus a wiggle bit away from a, then f of b, the slope of the secant line, f of b minus f of a over b minus a, well, that can be rewritten as the following. Instead of b, we have a plus h in both the numerator and the denominator. And what you see in the denominator is that the a's will cancel, and you get this beautiful result, f of a plus h minus f of a all over h. That should be hauntingly familiar to you. That is called the difference quotient. And it's also this guy right here. Let's go ahead and estimate the instantaneous rate of change for this function y is equal to the square root of x minus 4 when x is equal to 5. A couple things you need to note here. First, make sure that that input, x equals 5, is allowed to be an input for this function. That is, that x equals 5 is in the domain of this function. It is, but it's always good to start with that question. Now, if you're finding the instantaneous rate of change, really what you're doing is you're evaluating the slope of the secant line as these 2 points get infinitesimally closer together. I always recommend starting with relabeling y equals the square root of x minus 4 as f of x equals the square root of x minus 4. And then focus in on the fact that this is really just a slope. The instantaneous rate of change really, truthfully, is a slope. So you're saying, I need to know what the slope is, and the slope is, remember, f of b minus f of a all over b minus a. But again, in calculus, that b is often much better written as a plus h, because it's just a plus a wiggle. That's all it is. That's all that b is. It's a slight wiggle away from a. And now if you write it that way, you'll see that that denominator cleans up significantly. But the question is, what is a and what is h actually? Well, a is our anchor point. It's where we're trying to approximate the slope of the tangent line. If you look at the question, the anchor point is this guy right here. We're anchoring at x equals 5. That's where we want to find the instantaneous rate of change. So we're going to go ahead and let a equal 5. And this tells us that the instantaneous rate of change at a equals 5 is the following. So we get the square root of 5 plus h minus 4 minus 1 over h. It's minus 1 because f at 5 is 1. It's f at square root of 5 minus 4, which is square root of 1, which is 1. Now let's clean up that radical in the numerator. That's just going to be the square root of 1 plus h, and then minus 1 all over h. And then this is as h tends to 0. In other words, we have 2 points on a curve. Let's just pretend our curve looks like this because it actually does. So this is what our curve looks like. This is x equals 4 right there. And what we want to do is approximate the slope of our tangent line at x equals 5. That's really what the instantaneous rate of change is the slope of the tangent line at 5. To do that, really, if you're going to approximate, you need 2 points to find the equation of a line. All lines require 2 points. So this entire time, you're anchoring at 5, and you're taking another point slightly away from 5. 5 plus a little bit. And you're finding the slope of the line connecting those 2 points. And you're allowing those 2 points to get closer and closer together until they're almost touching. They can never really touch, because if you allow h to be 0, in other words, if those 2 points touch, you will be dividing by 0 here, and that's illegal. So you approximate it by letting h get really close to 0, but never actually becoming 0. Now let's go ahead and go to Desmos and see how this works. Now I'm going to do this in 2 different ways. I'm going to go ahead and start with the idea that we have the square root of 1 plus h minus 1 all over h. And I built a table in Desmos in the graphing calculator section. I just clicked on table here. I chose the input to be h and the output to be the square root of 1 plus h minus 1 all over h. And now we want that h to tend to 0. So let's go ahead and check that out. If you plug in 1, you can see what you get there in the table. If you plug in, let's say 0.5 or a 0.1 or a 0.01 and so on and so forth, you can go ahead and build your tables this way in Desmos very easily. You could see that the more zeros I put in there, the closer it looks to get to about a 0.5. Now it's worthwhile to check the negative values as well. So if you tried -1 and then -0.5 and -0.01, -0.001 or a few zeros and a 1, you can see that even from the left-hand side of 0, it is also approaching a height of, or the outputs are approaching a value of 1/2. So this implies, it doesn't prove, but it implies that our slope of our tangent line, or instantaneous rate of change, is going to be 1/2. Now, before I leave Desmos, I actually want to go ahead and show that this is not the only way you could have done this. This is a great way when you're initially working through calculus, but it's not the best way to do this style of problem. So I'm going to go ahead and set up a different way of doing this problem. First, note that I put in here the function f of x is equal to square root of x minus 4. And I'll go ahead and put in this, the point 5, 1. That point exists on our curve. It's just good to see. I'm going to turn off the grid here because that kind of gets in the way. So we see the point that we're interested in. We want the slope of the tangent line, or at least to estimate the slope of the tangent line at x equals 5. But to do that, we have to create a line. And the only way you can create a line is to gather 2 points, not 1. So we'll need a second point. And our second point we'll call b, f at b. It's just some point with an x value of b. I'll add a slider there, and I'll adjust this and say that our values of b can go between, let's just pretend, 4 and 6, with a step size of, let's say, 1/100th, just to really showcase this. And now if I move this, you'll see our point moves right there along with it. Now I'd like to put on here the line, the secant line that connects these 2 points. the equation of a line is always y minus the y value. I'll call it y sub 1 for now so that we can see this. And that's going to equal the slope of the line times x minus x sub 1, where y sub 1 and x sub 1 are the coordinates for a point on the curve. And we happen to know a point on this curve is going to have an x value of 5, for example, and a y value of 1. So that's our point 5, 1. Now we just need a formula for the slope between these two lines, or these 2 points, sorry. And you happen to know that the slope formula is the difference in y values, so 1 minus f of b, over the difference in their corresponding x values, so 5 minus b. And there we now have our secant line. You can see that moves very nicely. It's very beautiful. However, this doesn't actually tell us the instantaneous rate of change. It just gives us a really nice visual of our secant line. If you really want to see, maybe for different values of x here, maybe I'll go all the way to x equals 10, just to really showcase this. So if you want to see this for other values, you can extend that out if you want. But if you want to find the slope, you'll have to actually type in the slope formula again right here, just so that you can see the approximations for the slopes. So I'm doing the difference in the y values over the distance in the corresponding x values. And when you do that and you move b, you can see right down here the values of the slope of the secant line. And remember, as long as we drag that point closer and closer to our anchor point of 5, 1, we should get a better and better approximation of the slope of the tangent line. And you could easily see by what we did earlier that our table showcased that the slope of the tangent line is likely a half. Here, because we don't have such fine tuning on this, our values of b have a step size of 0.01, so they increment by 1/100th. You're not going to get a great approximation for your slope of your tangent line. To get a really better approximation, you could throw in a couple more zeros there for the fine-tuned detail. You'll have to zoom in quite a bit to really get a fine-tuned detail here. But once you do that, you can see, yep, as our non-anchor point approaches our anchor point from the right-hand side, it looks as though the slope of that secant line is approaching a half. In other words, the slope of the tangent line is likely a half. Same thing on the other side. So you can see that from the left-hand side, the slopes look to be approaching 1/2. There is a point on there where you get undefined, because if you let b, the second point, be anchored at x equals 5, where the anchor point is, you're dividing by 0 right here. And so that's the big trick in calculus, is that you cannot let those 2 points actually become one another. They have to actually be slightly separated. There has to be a little bit of airspace.
In the next example here, we're being asked to estimate the slope of the tangent line at x equals 0 for f of x equals the cube root of x. Again, same setup as the previous problem. Really, the slope of the tangent line is approximated using the following formula: f of a plus h minus f of a all over h, again, as h is tending to 0, as the distance between our 2 points is tending to 0. Our anchor point here is x equals 0. That's where we're trying to find the equation of the tangent line. So let's go ahead and substitute in 0 for a. F of h minus f of 0 over h, that becomes the cubed root of h minus the cube root of 0 over h, and that actually simplifies down to h to the 1/3 over h, which is 1 over h to the 2/3 power. And you could see a massive issue with allowing h to actually become 0 here. This is a really interesting problem, a very famous style of problem. And so let's go ahead and go over to Desmos to see what happens as h approaches 0.
Performing the same actions we did last time, we'll go ahead and add a table in Desmos. And I'm going to change, again, the input variable to be an h, and the output variable I'll call h raised to the negative 2 over 3 power. That's the same thing as h 1 over h to the 2/3 power. And we want, remember, to allow that h, which is the wiggle size, the wiggle away from x equals 0, we want that to tend to 0. So I will go ahead and start experimenting with h values that get close to 0, like with a 0.5 or a 0.1 or a 0.01 or a 0.001 and so on and so forth. Now, when you do this, you'll see that these outputs are tending to climb to positive infinity. If you tried a few more zeros here, I'll just throw on a bunch of zeros. You'll see this value is what, 215,000 and change. Let's see from the other side of 0. What if our wiggle wasn't positive, but instead negative? So again, I'll try a negative 0.5 and a negative 0.1 and a negative 0.01. And let's try a negative 0.0000001. You can see these values as h tends to 0 from the left-hand side is what we'd say. The outputs are tending again to climb to some massive number, and they'll continue to climb. So this tells us that as our wiggle size gets incredibly small, our output, which is representative of our slope of the tangent line or approximation to the slope of the tangent line, tends to positive infinity. Now, if you left this green dot on, you can see over to the right here that it showcases these points. They mean nothing to us, so I'm going to turn those off, and I'm actually going to graph the original function. I prefer to use x to the 1/3 rather than a cubed root just because it's a little bit easier. And let me see if I'm in projector mode. I'm not. I like to have projector mode on. And remember, we're trying to find the slope or approximate the slope of the tangent line at x equals 0. So let's go ahead and write in our anchor point. When x is 0, our function value actually is 0. So that's our anchor point. And you could label that if you want. You don't have to. And then let's go ahead and create a non-anchor point that will connect a line through. So we'll connect the line through b, comma f of b, and 0, 0 for our secant line. And we'll go ahead and say that b can be anything between, let's pretend, just -2 and +2. Try to keep it symmetric about our anchor point. And let's keep this finely tuned. So 0 point, the step size or increment size we'll have as 1/10,000th. Now what you can see is I can move this anchor point. Right? It goes kind of quickly through there, but there you go. And let's go ahead and graph the secant line connecting the anchor point, the black anchor point there, to the red non-anchor point. Remember, a line always has the form, or the equation of a line always has the form y minus a y value for one of the points on the line. And we know that one of our points has a y value of 0. And that is equal to slope times x minus the corresponding x value for that point that's on the line. But we would like to know what the slope is. So what I'm going to do is, you could type in the slope here, but I'm actually going to type it down here. I'm going to say that m is equal to. So I'm going to create a slope formula right here. And we happen to know that the slope of a line is a difference between the y values again. So f of b minus the y value of 0 over the difference in their corresponding x values. So b minus 0. And when you do that, you can see I get this beautiful secant line. And as these 2 points get really close to one another, I'll zoom in here. As these 2 points get really close to one another, you can see the tangent line almost becomes vertical. And that is indicative of the issue that we're seeing in our table. Our table says that as our wiggle away from our anchor point gets smaller and smaller, it looks as though our tangent line has a slope that gets more and more infinite, or larger and larger. And that's exactly what we're seeing here. This green line, which is approximating our secant line, is starting to get steeper and steeper. And in fact, let me turn off the axes here because it's really hard to see with that axis in the way. So I'm going to go ahead and show you that it does get very, very close, and then to a huge number of positive infinity. Obviously, you can't allow the anchor point and the dragged point to be the same value. And down here, you can see that the slope says 62.996, but in reality, if we were to decrease B a little bit more, now you can see that this is the problem with using a graph. There are strengths and weaknesses with using graphs and tables. The problem with using graphs on Desmos here is that your level of detail is very, very minimal. In fact, your stepping looks like by 1/100ths, which is not that great. But when you use a table, you have a lot more control. So the point here is that the slope of the tangent line seems to be approaching some hugely positive number that we would normally call positive infinity. And that is going to be a major topic for us as we move forward through calculus.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and